Hello everyone. In today's video I'm going to talk about the whole concept of electrostatic potential. And I just got over a cold, so if my voice sounds a little deep, that's why. But we're going to go ahead and dive right in. So what is electrostatic potential, or voltage as we commonly know it? Essentially, or fundamentally, it is stored energy due to forces between charged particles, much like gravity, how you can store gravitational potential energy between um, uh, the Earth and an object. You can store potential energy due to these electrostatic forces, and then you can release it and cause movement of charges, and that's fundamentally what is causing electrons to flow through a circuit and that sort of thing. All right, so let's think about electrostatic potential energy between 2 point charges, one positive, one negative, and they are experiencing a force of attraction. Now let's suppose that I grab one of the charges, and the positive charge, let's just say that's anchored, and I pull on the charge and I move it back. So it's like a spring that I'm stretching out. And I stretch it out just a little bit. We'll say this distance it goes from L to L plus DL. And what I'm going to do then is calculate the stored energy as I'm pulling this thing back. So the amount of force I will have to exert on this charge in order to get it to move will be equal to opposite the electric field force, so negative Fe. And from physics, you remember that work is force times distance, or more generally, force dotted with distance. So then you can multiply this out. Because the distance and the force are already in line, it just becomes multiplication there. So minus the magnitude of the electric force times dl there. And then you remember that from the definition of an electric field, we want to calculate the value of Fe. That would be equal to Q2 times the magnitude of E1, which is E1 is the field due to Q1. And then you just multiply it times dl. So that's how you calculate the amount of stored energy if you have two charges that are being attracted to each other, and then you hold them apart just a small distance. That's your incremental increase in energy.
Hey, Milan, what do you got there? Oh, is that an avocado? Oh, you like avocado, don't you? It's yummy.
Now that we know the work that has been done, or the energy that has been stored in this system, we can then use that to calculate the voltage. Remember that voltage is potential energy per unit charge, or joules per coulomb. So you can calculate, if you have two charges and you pull them apart just a little bit, and it increases the stored potential energy, you can calculate the small differential change in voltage as a result of that incremental increase in distance. And that would just be equal to the work done on that charge divided by the charge itself. And that cancels, this Q2 cancels, and so this gives a value of minus the integral of E dot dl. So if you move a charge through a path and you integrate minus E dot dl, then you can figure out the change in voltage, or the difference in voltage between those 2 points. So put mathematically, here you've got your differential change in voltage, that's equal to minus E dot dl. And if you have two different points in space and you integrate E dot dl from point 1 to point 2, you will actually get the difference in voltage, or the difference in joules per coulomb between point 1 and point 2. And I know that many of you are used to thinking about voltage in terms of like circuits between 2 points, but you can actually think of voltage as being between 2 points in space as well. Essentially, what this equation is saying is that if you take a certain charge and there's an electric field in the vicinity, and you move it from point 1 to point 2, the change in potential energy, in electrostatic potential energy, in going from point 1 to point 2 is going to be Q times V2 minus V1. And that is regardless of the path that is taken. And that is due to the fact that in electrostatics, when your charges are stationary, the field is a conservative field. And a conservative field means that the curl of E is equal to 0. And when that is the case, no matter what path you take, that change in potential energy will always be the same. One thing that you might be wondering is, if we're talking about voltages at like a point in space, where is your like ground potential, or 0 volts, if you will? Well, in electrostatics, by convention, we usually set point 1, or like our ground or 0 volt potential, as being infinitely far away from the system that we're working with. And that might be kind of confusing, but I hope to give you some examples to give you an intuitive feel for what that actually means. So we actually calculate the change in potential energy per unit charge when you go from being infinitely far away from your system to a certain point in the vicinity of your charges. All right, so let's try to derive the voltage coming from a point charge when you set your ground potential as being infinitely far away from the charge. So here we've just got the integral of E dot dl from infinity, r equals infinity, to some distance r from the charge. And we plug in that formula, standard formula for the field from a point charge. And so then we dot that with our dl vector here. And you work that integration out, you will get this, q divided by 4 pi epsilon r. So this is saying if you've got charge q and some distance r away, it means that the voltage at this point is equal to this when you set r equals infinity to 0 volts. So again, that might be a little bit confusing, but I'll give you an example that might clear things up a little bit. So here's our example. Suppose we have a 1 nanocoulomb charge here, and distance 1 meter away, I want to know what the voltage is at that point. So then I can just plug and chug with this formula, and it comes out to about 9 joules per coulomb. So the question is, what does that really mean for there to be a voltage of 9 joules per coulomb at a point? So I'm going to walk you through what that means. So one is, I want you to observe that if I place a 1 coulomb charge at that point, a repelling force would be experienced by that charge, because you have both positive charges. There's going to be a repelling force. Second point I want to make is that if the charge Q was fixed, then this 1 coulomb charge would start to move away, right? This is fixed, it's anchored, but that 1 coulomb charge I put there will experience a force, and if it's free to move, then it will go this way because it is being repelled. So as it's going out, the amount of kinetic energy, assuming the charge started stationary, the amount of kinetic energy that the 1 Coulomb charge would gain would be 9 joules of energy as R goes out to infinity. And so all of the potential energy would then be expended as R goes to infinity. And since that point was 9 joules per Coulomb, it means that if we just let it go, that potential energy gets released in the form of kinetic energy of the charged particle. So I hope that gives you kind of an intuitive feel of what it means to say that, oh, you have a charge here and the potential is this value. Now I want to talk about what would happen if you placed a -1 Coulomb charge there. So if it's -1 Coulomb charge, and you know you have 9 joules per Coulomb at that point, you would multiply the amount of charge, which is -1 Coulomb, times 9 joules per Coulomb, and that gives you an energy, potential energy of -9 joules. So let's think about what that means. So first, I want you to note that here, in this case, there would be a force of attraction being experienced between this positive charge and the -1 Coulomb charge. And what this means is that if you took the -1 Coulomb charge and you pulled it apart from r equals 1 to r equals infinity or far away, then the amount of energy or work that you would do to move that charge out would be 9 joules. And that makes sense, right? Because this point is at, or that charge was originally at -9, had -9 joules of potential energy, right? And we know that we set r equals infinity as our 0 point. So if you move from -9 joules to uh, -9 joules of energy to 0 joules, that's effectively gaining 9 joules of energy, which is the amount of energy or stored energy that you'd build up as you pulled away these two charges that are being attracted to each other. So I want to talk about why we even care about potential. So one of the cool things about potential is that it works a lot like electric fields, where if you have a collection of point charges and you want to find the total potential at a certain point, then the total potential would just be the sum of the individual potentials of the two point charges. And because potential is a scalar, um, you don't have to think about the actual like orientation of the charges relative to each other. The only thing that matters is the distance, and you can just add all these contributions up and find the potential at a certain point. If you know that, you can then use the general formula, this general formula that's always true in electrostatics, which is that the electric field is equal to minus the gradient of the potential. And taking this approach can oftentimes simplify the integrals that you have to do. And it does, you have to, there's an extra step then of having to take the gradient here. But oftentimes it's just more straightforward than having to integrate the electric field. So that's one motivation for working with potential. So I wanted to take the time to talk about the intuition for why this formula is true. There are plenty of textbook derivations you can look up, but I want you to really understand like why this is true. So we're going to go to a mountain analogy. I like my mountain analogies with talking about the gradient here. So suppose you've got this mountain here, and you have a ball here that you set at a certain point, and it can start rolling down the mountain. You can think of this height h as being proportional to the gravitational potential energy of this rolling ball. And it's analogous to the voltage here. You can think of the force experienced, the downward force of gravity on this charge, as analogous to the electric field. Now, if you remember what the gradient of a potential is it tells you the direction that you need to go that maximizes the change in potential energy. So this would give you, if you take the gradient of the potential here, it would give you the direction you need to go that is steepest, that is steepest. But we know in everyday experience, if I drop a, put a ball on a mountain there, it's going to naturally fall down the steepest path or the path of least resistance. So it's going to want to fall, or it's going to experience a force that is opposite or minus the gradient of that potential. And the same thing here is going on with the potential in the electric field. The force that that charge experiences, which has to do with the electric field, is going to be opposite of the gradient of that potential. So I hope that made some sense, and we'll encounter potential as we go on further in this course. But thanks for watching, and I will see you in the next video.